Hello students, in this lecture 10 of Foundation Advanced course, we are going to discuss about current electricity. So first of all, let's see what is electric current. Electric current is the amount of charge flowing through an area per unit time. So the electric current is equal to charge flowing through an area divided by the time taken for that charge to flow through the area. So let's say in time t, a charge q is flowing through the area. Then the electric current which is flowing through the area is going to be equal to q by t, correct? Now the unit of current is ampere, and 1 ampere current means that 1 coulomb of charge is flowing through the area or the cross section in 1 second. The direction of current flow is opposite to the direction of electric flow. Conventionally, we take that the direction of current flow is opposite to the direction of electric flow. You know that these electrons are negatively charged particles. So here the negatively charged particles or electrons are moving in this direction. This is the direction of electron flow, and the current flow is opposite to the motion of this electrons, that is negative charge, in this direction, which is the direction of current. Or we can say that as the negative charge is flowing in this direction to the right, the current is flowing to the left. Now let's move on to the next one. So let's discuss about Ohm's law. Ohm's law states that the current flowing through an object is directly proportional to the voltage across the object. So it says that I is the current flowing through the object is directly proportional to the potential difference or the voltage that is applied across the object. So here if we increase V, the current which is flowing the circuit I will also increase, and if you remove this proportionality sign, we'll get the equation like this: I is equal to V by R, where R is known as the resistance of the resistor. This resistance opposes the flow of current, and if an object has higher resistance, there is less current, and if the object has smaller resistance, the amount of current for the same voltage is going to be larger. Unit of resistance is ohms. When you apply a potential difference of 1 volt across a resistor and a current of 1 ampere is flowing through that resistance, then that resistor is said to be of 1 ohm resistance. Okay, now let's move ahead, students. Now we are going to discuss about resistance. For a resistance which, let's say, look like this, for this resistor, if the cross-sectional area is A, the length of this resistor is L, and it is made up of a material which has resistivity rho, then the resistance of the material is going to be R is equal to rho L by A. So resistance is directly proportional to length, correct? Resistance is directly proportional to length. It is inversely proportional to cross-sectional area and also directly proportional to the resistivity of the material. So if we increase the length of a resistance by 2 times, its resistance will also increase by 2 times. If we increase the surface area by 2 times, the resistance will decrease by 2 times. And if we change the material to some material which has higher resistivity, the resistance will increase. And if we change the material with a material having lower resistivity, the resistance of the object will decrease. Now let's move on to the next one. In this one we are going to discuss about combination of resistance. There are two kinds of combination of resistances. One is series combination and one is parallel combination. In series combination, we connect the resistances like this. In this case, a current flows through the resistance like this, and the current is same across all the resistors, but the potential is not same across all the resistors, and the net or equivalent resistance of this combination is equal to R1 plus R2 plus R3. If you see here, you can see that this R equivalent is going to be larger than R1, R2, R3 or any other resistance that is present. So the net resistance in the series combination is the sum of the individual resistances, and it is larger than any of the individual resistance. Now the next kind of combination is the parallel combination. In parallel combination, resistances are connected end to end. The potential across all the resistance or the voltage across all the resistances is equal in this case, but the current across the resistances are not equal to each other. In parallel combination, the equivalent resistance is given as 1 by R equivalent is equal to 1 by R1 plus 1 by R2 and so on. The equivalent resistance is smaller than all the resistances. So the value of equivalent resistance is even smaller than the smallest resistance that was present here. Here we are going to discuss about resistivity. The unit of resistivity is ohm meter, which can be easily derived using the formula. We know that R is equal to rho L by A, correct? So I can say that rho is equal to R A by L. So let's put the units here. Resistance, which is ohm, area, which is meter square, divided by length, which is meter. The unit of resistivity is ohm meters, correct? The resistivity is not dependent on the area or the length of the material or even the resistance of the material. The resistivity of the material is only dependent on the material which is used. So if you have iron, you will have different resistivity. If you have copper, you will have different resistivity. If you have water, you will have different resistivity. The resistivity of material increases with temperature. So for a conductor, when you increase the temperature, the resistivity of the material will also keep on increasing. Now we are going to discuss the heating effects of current. We all know that when an electric current flows through a wire, it heats up. The amount of heat energy that is dissipated in a wire is directly proportional to the square of the current, also to the resistance of the resistor and the time. So the amount of electric energy that is dissipated is equal to I square RT, where I is the amount of current that is flowing through the resistor, R is the resistance, and T is the time interval. Now let's look at this formula, which is equal to I square RT. Now what I can do is, instead of this I square, I can write I into IR times T, which is equal to I. Now this IR is equal to the potential V, correct, VT. So this is equal to VIT as well, right? One more thing that I can do is, this I is equal to V by R. So this is equal to V by R times T. So this comes out as V square RT. So these are the formulas that we are going to use for the energy dissipated in the resistance I square RT, VIT and V square RT. Now let's move to the next one, which is electric power. Electric power is basically rate of dissipation of heat. Electric power is basically the rate of dissipation of heat energy in a circuit or in a resistance. So this power P is equal to heat dissipated upon time, okay? Upon time. Now heat dissipated, as you know, the formula was I square RT, dividing it by T, I get the formula I square R, and the other formulas are, it is equal to VIT divided by T, and also equal to V square by R. This is the amount of power that is delivered to a resistance, or the amount of power which is being delivered by a battery. Thank you students, that is all. This marks the end of our foundation advanced course. All the best.